All right. Good morning, everyone, or good afternoon, depending on the time you're watching this recording. I'm John Ramirez. I'm part of the group 4 in our research methods class this semester, spring 2026. And alongside me today are Noah, Avian, Matthew, and Maria. And we're going to be talking about additive manufacturing of TPMS heat exchangers for marine thermal management. Now, TPMS stands for triply periodic minimal surface. Um, Try saying that 5 times in a row. But what we're going to be doing today is going over what the concept means for the marine environment and their challenges. Now, our focus is really on laying a lot of the foundation to bringing this technology out of the concept stage and characterizing what challenges might look like in a real world application. So for this project, we're going to be focusing a lot on the feasibility and the geometry definition and corrosion characterization. So just looking over the presentation agenda, just a brief overview of what we're going to be talking about over the next couple of minutes. Um, is We've got the challenge. We're looking to see what's the issue with just using our standard TEMA shell and tube heat exchanger options. You might be saying, John, I just learned about this the other semester. What's the big deal? Well, we'll go over what's up with that. Of course, we're gonna also just talk about the alternative. We think you might just be like, if you're a big time marine customer, you're thinking, man, I need something better than what we have already. So what's out there? We'll stay tuned. We'll talk all about TPMS. And then three and four, I've kind of already hinted at that we're interested in laying the groundwork for understanding these new structures, but we'll talk about how we're thinking about doing this and our proposed methodology. Then, of course, Noah, we'll talk about the knowledge gaps we'll be tackling, the magic sauce we're kind of going to bring to the table. And last but not least, definitely hit some areas of what we think our scope will increase to and impact other areas around the world.
So, why are we doing this? So, currently, the marine industry relies on standard shell and tube heat exchangers. They have been a go to for decades, but they have major drawbacks. Firstly, they are bulky. On workboats and recreational vessels, they just don't have the luxury of extra space. And secondly, these systems are constantly fighting a losing battle against seawater between saltwater corrosion and biofouling like barnacles and algae. um, these units just degrade quickly because they're often just tucked away in tight engine rooms. um, Keeping up with the maidens is really a nightmare, so essentially the old designs just can't keep up with the modern demands. So this is where the TPMS, or the triply periodic minimal surfaces, come in. um, and as you can see from these shapes in this picture, we're moving away from the traditional tubes and toward these complex structures that are sponge-like structures. So by using these geometries, we can actually see 150% boost in efficiency compared to the old shell and tube models. And I would say that the secret here is the flow path of these geometries, because the water has to weave through these intricate curves of inside these geometries, and that maximizes the heat transfer in a much smaller footprint. Of course, you cannot build this something like this so complex with traditional tools. That's why we're looking at using laser powder bed fusion, which is essentially 3D printing but with metal, so that we can make these designs and intricate geometries an actual reality.
So with the context established, here are the objectives and outcomes we aim to achieve. We're characterizing laser powder bed fusion fabricated TPMS structures across 3 dimensions: thermal performance, pressure drop, and corrosion resistance. By doing so, we establish the framework for designing and understanding the characteristics of this manufacturing technique for heat exchangers operating in open-loop seawater service, a combination that is yet to be characterized. To do that, we will utilize a methodology that breaks down into 3 phases that build on each other. Starting with design, we'll define 6 TPMS geometries optimized using CFD at marine scaled Reynolds numbers. And before committing to metal fabrication, we'll validate those models using PIV on clear resin SLA prints with refractive index match fluid, a proven method for inspecting complex internal geometries like TPMS structures. Once the models are validated, we will fabricate the final heat exchangers in 316L stainless steel via laser powder bed fusion. From there, we'll move into thermohydraulic characterization. Pressure sensors at each inlet and outlet log pressure drop across each configuration at various flow rates. And coupled temperature sensors with measured mass flow rates allow us to calculate the energy transfer from one medium to the other. Finally, for corrosion analysis, visual inspection has real limitations inside these geometries, so we will be using electrochemical methods such as EIS or potentiodynamic polarization to identify and distinguish between pitting corrosion and MIC at the material level.
In lab testing, TPMS-based heat exchangers show exceptional thermal performance. But as of right now, their behavior under the combined mechanical, thermal, and corrosion demands in marine applications remains an unknown. We plan to close this gap by answering several pertinent questions. Previous work has covered numerical analysis in marine applications. Where we differentiate our work is with the inclusion of flow structure and thermal validation techniques on parts designed specifically for marine applications. One of the most impactful gaps that we will be covering is understanding the different corrosion mechanisms that are present in a laser powder bed fusion part used in a marine application. More specifically, we will be able to understand the impact of the grain structure and the surface finish on corrosion. Laser powder bed fusion creates microstructures with fine grain boundaries that behave differently than wrought 316L stainless steels that have been studied in previous work. Between these grain boundaries are microscopic slag particles that act as pitting initiation sites in chloride-rich environments like seawater. The surface finish is also an interesting parameter that needs to be studied because a laser powder bed fusion part has a significantly higher surface roughness than a wrought part at 10 to 30 micrometers and 0.14 to 1.2 micrometers respectively. And this elevated roughness inversely correlates with pitting potential. Meanwhile, the potential for microbial-induced corrosion rises significantly as roughness increases due to the increase in biofilm adhesion sites. Our final gap to cover is that we will essentially be writing the book on proper laser powder bed fusion part integration within marine thermal fluid systems for future design engineers to use as a reference as they create the next generation of thermal systems for the marine sector.
So why does this research matter? First, we're solving a real problem in the marine industry. Small vessels like workboats and recreational craft need compact, efficient cooling. Validating these TPMS heat exchangers will provide a direct alternative to the industry standard, enabling adoption. To succeed in this goal, collaboration with industry partners will be essential, assuring their needs and desires are understood and addressed. Second, this project is about people. During the development and completion of this project, 5 graduate students will gain direct hands-on experience in advanced manufacturing, fluid dynamics, and corrosion science. These skills will be critical for addressing future engineering challenges in their careers. Third, the environmental impact. The shipping industry is a massive contributor to global emissions, accounting for approximately 1 billion tons of CO2 annually. The adoption of more efficient heat exchangers directly supports the global mandate to reduce the carbon footprint of the industry. Even a small increase in efficiency, multiplied across thousands of vessels, can significantly reduce fuel consumption and emissions. Lastly, we hope the data we generate during this project will serve as a technical foundation for future research. Our results will be shared in peer-reviewed journals and technical conferences. By doing so, we aim to share our design guidelines with the entire engineering community, accelerating innovation across the field. In summary, this project tackles advanced manufacturing and outputs a practical solution that is good for the industry, the workforce, and the planet.